and welcome to Astro Adda, our Saturday astronomy meet. And today we have with us Dr. Manonita Chakraborty, who's at IIT Indore. And very happy to welcome you, Manonita. Thanks for coming. So I'll just briefly introduce her. Dr. Manonita is an assistant professor at the Department of Astronomy, Astrophysics, and Space Engineering at IIT Indore. She's interested in the study of compact stars and their observational characteristics. Her research focuses on the physics of neutron stars, black holes, pulsars, GRBs, X-ray flares, ULXs, etc. So today Manonita will be talking to us about the many phases of stellar remnants. And welcome. And over to you, Manonita.
Thank you, Priya. So it's a pleasure to be here and talking about this very interesting stuff. I hope you are all doing well, and we'll spend a fun evening talking about the most exotic objects, at least to me, and how they behave and their different characteristics. So today I'll be talking about many phases of stellar remnants. What are stellar remnants? They are the compact stars that are left behind, or the compact stellar cores that are left behind once a normal star finishes its life cycle. For the purpose of this talk, I will be mainly focusing on these three categories. This is the neutron star, this is a black hole, and this is a particular class of neutron star which we know as pulsars. Okay. Just a second. Okay. So just to give you a brief context, so this is where we start, where we have the star-forming nebula, where the first stars are formed. The stars are formed, and once the stars are formed, they go through their normal life cycle phases, behaving like a sun-like star or a similar star with much more massive mass or luminosity, which you see here. So, as the sun-like star finishes all their fuel, which in the case of sun is primarily hydrogen, by finishing the fuel, I mean when they stop having enough hydrogen which they can fuse to helium inside their core so that they can give luminosity, such stars turns into red giant, and where they become extremely luminous, and they increase in size much more, and finally goes through a planetary nebular phase, giving rise to a white dwarf. What happens to the stars which are much more massive? What do I mean by more massive? Which have masses at least 8 to more than 8 times the solar mass, or the mass of the sun. So what they do is such stars spend their fuel much faster than any sun-like star, and very quickly go into very giant or supergiant stars, which then go into a supernova phase, giving rise to these two very exotic objects which we know as neutron star or black hole. Whether it will be a neutron star or a black hole, that totally depends on the initial mass of the parent star. So today's talk will be primarily talking about this neutron star and black hole that are formed at the very end of a massive star's life cycle. So this is what happens so when a massive star undergoes a supernovae. So let's say a massive star had a total mass of 20 solar masses. So when he finishes its life cycle and undergoes a supernova, it throws away most of its mass in a blast wave, which we know as the explosion, which we know as a supernova, where most of the materials will be thrown out, which you see here as the very brightly radiating and nice looking nebulae. Here you see the Crab nebula, and only the core of the massive star is left behind as a compact star somewhere here as a neutron star or a black hole. In this case, it's a neutron star. So first let's take a brief introduction about what actually are black holes and neutron stars. So black holes are basically the object that is left behind when a complete collapse of star happens, meaning there is nothing, no outward force that is present which can balance the immense gravitational inward force of the star, and then the star completely collapses to such a point that at the very core of the star, there is something present which we call singularity, which has zero radius but infinite density. This is a very tricky concept, and we physicists tend to not talk about it, bypass it, and look at the black hole from a more outward point of view and talk about the total characteristics of the black hole. So typically, the parent stars which have masses more than 20 solar masses after undergoing supernova tends to form a black hole. Typically, the kind of black holes till now we have seen in the electromagnetic wave band ranges, the masses of them ranges from 4 to 20 solar masses. Here is the first direct image of a black hole, which you must have seen many times. That was taken a few years back. Though this is a different kind of black hole we are talking about. This particular black hole was a supermassive black hole, which tends to be in the center of galaxies rather than forming at the end of a star's life cycle. But let's come back to the stellar black holes. Stellar black holes are those which forms after the life cycle of a main sequence massive star. Sorry, after the life cycle of a massive normal star. So, uh, of course, black holes by definition are very interesting because these are the objects where gravity dominates any other existing forces. But by definition, black hole is black. Their gravity is so strong that nothing, not even light, can escape. Huh. So the question is, how can we detect such objects, and how can we uh, try to infer any physics of such objects? We'll address these issues in the next part of this lecture. One easy definition to talk about when defining the size of a black hole is something called the radius of a black hole. And the radius of the black hole can simply be calculated by taking the point at which the velocity of a particle escaping the black hole's gravity equals the speed of light. In other words, not even light cannot escape. So if you equate that, one can very easily get how big, how massive, not massive, but how large in size a black hole will be. And this particular radius, in the most simplest cases, is called the Schwarzschild radius, which also in the most simplest cases gives you the event horizon of a black hole. A easy way to calculate, as I said, the event horizon is the point at which the escape velocity of a particle, which we know as the square root of 2 gm by r square, where m is the mass of the gravitating object, equals the speed of light. So if we put v equals to c, this will give us a total radius of r equal to r equals to 2 gm by c square. And this can be written as 3 kilometer m by m solar. So if typically, let's say a black hole has 5 solar mass, then this Schwarzschild radius, the radius of the black hole, will roughly come down to be about 15 kilometers, which is a very small radius. Remember, we are talking about 5 solar mass, a mass of 5 solar mass, which is 5 times the mass of sun, totally compactified into a radius of only 15 kilometers, a rough scale of a city. So, which results in a very strong density and in turn a very strong gravity. That makes it one of the most interesting exotic objects to study, the effects of gravity. The other class of objects that I will be talking about, in certain sense, they are even more exotic, which are called the neutron stars. So neutron stars are uh, objects which have roughly 1.4 solar mass, and they are not completely collapsed like the black hole. They are formed when a parent star, which has a typical mass of 8 to 20 times the mass of a sun, undergo a supernova explosion and collapse to form this particular stellar remnants, this particular cores. In the case of neutron star, what happens is that we have two forces. One is the inward gravitational force, which tries to collapse the star. Some force has to balance this particular strong gravitational inward force. What is it? In this case, that particular force is the force, a quantum mechanical force, that is uh, given by the degenerate neutron. So basically, due to the high density, we have a large sea of free neutrons present inside the neutron star. And as the density increases, neutron stars filling up all the low energy quantum states. And as all the energy states gets filled up, in turn, the energy increases, the pressure increases, which results in an outward force. This is called degenerate pressure or degenerate pressure. And this degenerate pressure is an outward pressure which balances the gravitational inward force. So neutron star, in one sense, they are more easily observable because you can see the radiation coming from at least the surface of the neutron star, and you can probe very close to the neutron star, unlike the black hole. They have a typical radius of 10 kilometers and a mass that can vary from 1.4 to 3 solar mass. Again, the entire mass of, let's say, 3 times the mass of a sun compactified into 10 kilometers, which is roughly the uh, length of a city, dimension of a city. The density, interestingly enough, of a neutron star can go as high as 10 to the power 14 grams per cc, and at the very core, it can go even higher than the 10 to the power 4 grams per cc density, or even the nuclear density. So imagine, we know the inside the nucleus of an atom, the density is the highest. That's the most compactified thing that we know of that forms matter. But inside the core of a neutron star, the very core of a neutron star, the density can become even higher than the nuclear densities, and such high densities can result in very exotic states of matter, displaying superconductivity at millions of degrees of Kelvin temperature, and superfluidity, and even further exotic states of matter which are not terrestrially observable or understood at all. Huh. Even quarks, which we know that builds up the protons and neutrons and cannot exist in a free state, they are also made to be free and distorted into various different exotic states of matter. So this makes the study of neutron star extremely interesting physics to pursue. Uh, because of the high density, a simple uh, teaspoon of neutron star matter can weigh as high as billions of tons. So that makes the matter very exotic, not only from the astrophysical point of view, but also from the material science and particle physics point of view. On top of that, neutron stars that we see normally are spinning very rapidly. They can spin as fast as 600 times per second. So you can imagine that if you are sitting, luckily enough, you are sitting on the surface of the neutron star, the velocity that you will experience can reach very close to the velocity of light, which can have very interesting consequences. And last but not the least, neutron stars tend to have very, very high magnetic field. The most highest ultra strong magnetic field in the universe, which can come up with interesting consequences. We will discuss more about it in the very later half of the talk. So, uh, let's hope that I have convinced you that these are indeed very interesting objects to look for. So, let's talk about how do we look for them practically, observation, because uh, these are very interesting, but till 50, 60 years back, nobody knew about them. They have been proposed since ages, since the discovery of neutrons, let's say, or since Einstein proposed the general theory of relativity. Black holes were proposed, but for a long, long time, there was no actual detection, at least not even of neutron stars. They are very difficult to look for because in normal optical wavebands, they are not bright at all. So let's say the total luminosity that we were getting from such an object is 4 pi. It's thermal radiation, and it can be written by using the Stefan-Boltzmann law as 4 pi r square sigma t to the power 4. Then, then uh, for a typical white dwarf, let's say, which is a little bit bigger than the neutron star, which has a radius of 6,000 kilometer, which is also a type of compact star, and temperatures are very hot and temperatures of 10,000 Kelvin. And the wavelength at which their luminosity peaks at is not the optical wavelength, but indeed the X-ray wavelength. They are very energetic, highly luminous, but not in the optical, but in the X-ray. So when the X-ray astronomy started, from there onwards, uh, the X-ray sky opened up to us when we started detecting thousands and hundreds and thousands of such interesting objects in the X-ray, and many of which were either black holes or neutron stars. Here you can see such an example, though this is neither a black hole nor a neutron star, but a similar kind of object, which is called a white dwarf. And this is a very nearby star, which is called the Sirius A, which is the brightest star in our galaxy. This top image is in optical. So here you can see that Sirius has two stars, two binary stars. This is the Sirius A, which is a normal star, sun-like star, a little massive than sun. And there is a small dot, almost barely observable. But if you look in X-rays at the same object, the picture completely reverses. In this case, this is the small object that you are looking at. This is called Sirius B, and the small one is a normal star. It's called Sirius C. So it's more brighter in X-rays, which immediately tells you that they are much hotter, following the temperature wavelength relation. They are much hotter, and in the case of neutron star, they are even more hotter. So, which tells us we have to look for these objects in X-rays. Just to give you a comparison, this is the image in optical, and this is how the image of a neutron star looks in the optical. It's barely visible, barely. Huh. But later on, we will see X-ray images where they are much brighter, much luminous, and so X-ray spectroscopy and X-ray imaging are the way to go when we're trying to look for black hole or neutron star type of objects. Also, what else we the first discovery of such objects was done using an X-ray satellite called Uhuru, which detected the pulsate, the kind of regular variations from a particular neutron star, which gave such periodic variations in X-rays. So this was the first X-ray pulsar that was detected by the satellite, which tells you not only that are neutron stars, not only they emit in X-rays, but also interestingly enough, the emission that we see from these objects are not very continuous or not very stable, and they are highly variable. And not only that, the variation is often seen to be modulated by the sinusoidal pattern, which corresponds to the motion when an object moves in a binary orbit with another object. So that tells us this particular object that was observed was actually, of course, a pulsar, but on top of that, it was in a binary orbit with another object, which resulted in the going to and forth from our line of sight, resulting in the sinusoidal orbital modulation. So there is a companion to that, and later on we'll see that most of the neutron star or the black hole objects that we see in our X-ray sky are in some companion orbit with a star, and that results in the their first of all their orbital motion and their emission as well. So, what powers this object's emission? How are they so bright in X-ray? They can have millions of Kelvin temperatures. Huh. Why are they so bright? So, the fact that we have just said now comes into play here. So these objects are often in a binary orbit with another companion star. So this is the picture we are talking about. Here you can see the image of a cluster of stars in X-rays. This was taken by Chandra, and all these bright objects that are circled are a neutron star or a black hole source. And typically, if you could zoom into them, unfortunately they are so far away and so small, we cannot really image them. But ideally, we can reconstruct their physics just by looking at their other characteristics. So ideally, what we will see if we could zoom in is that they are in a binary orbit. Here there is a neutron star or a black hole. They are in a binary orbit with another normal star. Normal star meaning a sun-like star, which may or may not be more massive than sun, and which is uh, going through the normal nuclear fusion processes in its center. And there is a strong neutron star or a black hole sitting there. Because the gravity of the neutron star and a black hole is very, very strong, what it does, it starts pulling matter away from this main no, companion star. And because this matter has angular momentum, instead of falling directly on, it kind of spirals, forming a disc-like structure, which we call accretion disk, and eventually falls on the surface of the uh, black hole or a neutron star. Now, as it falls, it has to lose a huge amount of gravitational potential energy. Ideally, let's do this simple exercise. Uh, let's say, let's assume a proton or a hydrogen atom. Uh, Assume that it is falling from infinity to the surface of a black hole. We have just calculated a few minutes back. The surface of a black hole is given by the event horizon or the Schwarzschild radius, which is given by 2 gm by c square. Let's say a typical black hole have 5 solar mass. Huh. So if we plug in this number, the total energy that is released is of the order of 0.1 mpc square, and this falls bang in the X-ray wave band. So that immediately tells you why this object has to be luminous, in the X-ray wave band. And not only that they are luminous in the X-ray wave band, but the total amount of energy that is released, that is also one of the most extreme energy efficient processes, because of the change in potential energy that we have just calculated. This is obviously a very idealistic calculation, but even if you do a precise calculation, numbers are very comparable. So that tells you the accretion, this process of spiraling on towards the central compact star is called accretion. So accretion is typically the most efficient source of energy generation, not just for the case of compact stars, but if you even compare with the nuclear energy generation rates per unit mass, this is way higher than the that is observed in the case of nuclear reaction going on. So this makes them the most brightest objects in the X-ray universe. This is how it looks like. Typically, this is an artist's impression, whereas the main sequence star is getting accreted by the central small compact star that is sitting there. The accretion disk, because as I said, the release of gravitational potential energy is very high. Change in gravitational potential is very high. They can reach very high temperatures and can reach up to 10 to the power 7 K, which makes the emission from this object coming mostly from the disk. So this is the picture we are talking about, and why this is interesting, because as the matter falls towards a compact object through this accretion disk, it comes very, very close to the central compact star. And near the central compact star, the gravity is very, very strong. As the gravity is very strong, uh, it various phenomena that we cannot see, even in the case of very massive stars, comes into play here, because gravity can truly reaches its strongest region, and several theories of gravity that cannot be tested, because remember, gravity is a very weak force that cannot be tested in any other scenarios, can very well, I won't say easily, but very favorably tested in the uh, regions of the accretion disk, and you can compare against the different models of theories of gravity that have been there, and even test the various prediction of the general theory of relativity. Also, as I said, inside the neutron star, the matter can reach very exotic conditions, and we do not know how such exotic matter behaves. Superconductivity at very high temperatures, and then freak quarks and exotic pasta phases, we don't know. Huh. So theoreticians, high-energy physics has proposed how such matter behaves, and there are various equations of state. But there are various several models. We do not know which one is the correct because we cannot probe inside this core of a neutron star. So, in order to understand how matter behaves at such exotic, ultra high densities, there are several equation of state of those matter. Like we know the ideal gas equation of state. In this case, very different kind of equation of state has to be employed for this exotic matter, and that has been proposed by the theoreticians. And all these lines that you see, all the green and the blue lines, are the different theoretically proposed equation of state that describes the nature of the matter, and that has been translated into the mass versus radius phase. And interestingly enough, if we can very correctly measure the mass and the radius of a neutron star, we can rule out one or many of such equations of state, which will in turn give us the nature and the behavior of matter under this very exotic density conditions. Of course, as I've already told you, the gravity, this on the y-axis we have how strong the gravity is, which is given by the something called the curvature, and on the x-axis here we have the total gravitational potential, and various objects are plotted on this axis. And here you can see the neutron star and the black hole XRBs uh, uh, occupy the strongest curvature or the strongest gravity region of this diagram, telling that if you really want to probe and compare different models of gravity, neutron stars and black holes are the way to go. And we can rule out the predictions of various uh, corollaries of general theory of relativity, and any other for the different alternate theories of gravity as well. So, so let's talk about observations. Now, I have told you that these objects are mostly bright in X-rays, but interestingly enough, they do give emission in all wavebands to different varying degrees. So this is the picture of the X-ray binary that I have painted with you to you. That there is an accretion disk and a central black hole or an neutron star sitting there. There is a jet, and each region of this system gives rise to emission in the different wavebands, starting from radio, which typically comes from the jet, to X-rays, which typically comes from the disk and any regions very close to the central object, which is way much hotter. Huh. So, in order to truly understand the nature and the emission physics of this object, we need to not only look in X-rays, but we need multi-wavelength broadband studies where we can look at different emission regions and different emitting regions of this system, giving radiation in the different wavebands. And that's what is happening currently nowadays. Also, another interesting point that one should always remember when dealing with this kind of sources, which I have briefly mentioned, but this is an example of that. In the x-axis we have time, and on the y-axis we have intensity, as observed by different instruments in different energy bands. And as you can see, that these objects are not just highly luminous, but they are also highly variable. You can see that within the span of a few hundreds of days, what kind of different pattern they can trace out. So this tells us two things: that we need to observe in many wavebands, and we need to observe many times, and with as uh, fine precision, time precision as possible. Because this variability are also related to various physics happening in the system. By system, I mean they can be related to the instabilities that are happening in the accretion disk that I talked about, or there can be a very high energetic gas present on the top of the disk and the central compact object, which is called corona. And the corona can also be very highly variable, resulting in such strong patterns. Variability is also strongly dependent on the energy itself, which energy band you are looking at. Here you can see that in different energy bands, these are three different energy bands, the variability is looking slightly different. This variability is not just observed for the stellar classes, but just to give you the bigger picture, this was actually observed for the case of the supermassive black hole, which was observed by each. That was not a single image. They took the image over a few days, April 5, 6, 10, 11. And if you look at these four images very closely, you will see variations in the intensity distribution among these four images, which tells you all these kind of accretion involved objects can be very highly variable. So that tells you broadband simultaneous high resolution, high time resolution observations are indeed the way to go forward. So, so what kind of emission we are looking for from these sources? So here is a black hole or a neutron star sitting here, and what we see when we see the emission coming from these objects is basically an accretion disk. This gray region is the accretion disk, because typically the density of the accretion disk tends to be high. Uh, uh, the emission that comes from the disk is thermal. It reaches thermodynamic equilibrium and can be typically modeled by a thermal emission coming at a temperature of around 1 kV or 0.6 kV. Now, not just the disk is there, but there is a hot gaseous plasma present all around. This is something what we call corona. This corona is also present there. And what this corona does is all the photons that are coming from the disk, all the thermal photons that are coming from the disk starts interacting with this very hot corona. And when it interacts, they interact via various processes, the primary of which is the uh, inverse quantization process or the quantization process, and that is a non-thermal process, and that often upscatters the photons, moving them to higher energies. So let's say 0.6 kV X-ray photons were coming from the disk, which interacts with all the high energetic electrons in the hot plasma, and the amount of the photons that leaves this corona have a much higher energy, starting from 10 kV to even higher, a few hundreds of kVs. So that can be a very accelerating process that can increase the energy. And detailed modeling, here you can see an actual spectra that was taken by one of our own very own satellites, AstroSat. The good thing about AstroSat is it has a very broadband coverage. We just discussed that we need a broadband view to actually study the complexities of these objects. So, what AstroSat gives you is a very broadband window, and using this broadband window, one can look at this object starting from the very 0.7 kV to almost 80 kVs. And here you see such a neutron star LMXP, the spectrum of a neutron star LMXP. And it has two components given by this dashed lines, one corresponding to the thermal emission that is coming from the gas, another this comptonized high energy photons that comes from the corona. By carefully modeling this spectra, one can predict a lot, infer a lot about this X-ray binary system. This is called X-ray binary, and one can talk a lot about what is the innermost disk radius, and consequently, if this innermost disk radius is related to the uh, event horizon, one can measure the event horizon of the central compact object as well. Particularly, that is very interesting in the case of black holes. Along with that, the mass and spin of the central compact object can also be measured using the spectral modeling methods. Also, I have been talking about spectrum, but I have been talking about the timing variabilities as well. So, in terms of timing variabilities, there are also very interesting features. Here you can see the power spectrum, the Fourier window converted into the power. The power spectrum versus the frequency, which basically tells you an idea of how much variable at a particular frequency the object is, the, uh, the source that you are observing. And interestingly enough, in the power spectrum of this neutron star and black hole NMXP sources, extra binary sources, we often see these strong features, periodic, almost looks like periodic, but they are called quasi-periodic because if it was completely periodic, it will be a single line corresponding to a particular frequency in the power spectrum. But in this case, it has a sufficient width, so that is why they are called quasi-periodic oscillations. And they are very interesting timing features alongside the spectral features. They span a wide frequency range starting from millihertz to kilohertz frequencies, and often seen uh, entwined. So here you can see two peaks. They are often observed in such a manner where two peaks are observed back to back. These are extremely interesting because uh, in the case of both neutron star and black holes, this can be directly related to various features of their corresponding uh, gravity. And using that, one can actually directly calculate certain features of the space-time around such strongly gravitating compact objects. Hmm. For neutron star X-ray binaries, the kilohertz QPOs, the QPOs in the kilohertz range are more frequently observed, whereas for black hole cases, the frequencies tend to be a little bit on the lower side. They change, they are not always present. They're very variable and change very quickly with the uh, luminosity of the source, how bright the source is, and various trick signatures of gravity can be observed from such sources. Here is another example. Um, Again using AstroSat, here you can see the similar kind of QPO, but this time not in the kilohertz range, but in the millihertz range. So the where do they come from? So the idea is that when you are looking at the X-ray binary source and looking at the emission that is coming from the accretion disk, the disk can be perturbed because of various reasons. First of all, let's say there is a blob present at certain regions of the disk, then uh, uh, the blob, whenever and the blob is rotating because the accretion disk has an angular momentum, and whenever the blob is coming back, it will give rise to a certain periodic feature. And let us assume that the rotational nature in the accretion disk is Keplerian. By Keplerian, I mean we can equate the centrifugal force with the gravitational force. If we can do that, then the frequency of the orbital blob can be written in this manner. Right. Now, let's say the blob is at a radius which is the innermost possible radius of the disk. Below that radius, there cannot be any particle in a stable orbit. This is a very classic typical radius which we call the innermost stable circular orbit. This is the minimum radius at which around a compact star a particle can be in a stable orbit. So if the blob is at this innermost stable circular orbit, then just by measuring the frequency, one can measure this particular radius, and that will give us the radius of the ISCO. Now, the ISCO radius is very strongly related to the event horizon radius for both neutron star and black holes. Particularly for black holes, that becomes very interesting because that gives you a way to measure the event horizon of a black hole. Particularly for the stellar case, where you cannot directly image the object. This is for kilohertz QPOs. For low frequency QPOs, things can be of different type but equally interesting. So for low frequency QPOs, what we attribute them to is something called the lens steering precision for the case of black holes. So what happens is that these black holes here are very, first of all, very strongly gravitating, compact star, and they also have a spin. So as they are a very strongly gravitating object with spin, they, when they rotate, they drag this nearby space-time along with it. Uh, the space-time that is close to it. and this is called a frame dragging effect. They drag the entire space-time around the black hole around with it, and whenever the particles that are sitting around the black hole in that particular regions of the space-time, the particle in that regions of the accretion disk tend to kind of oval. Huh. As the frame gets dragged into the spin gravitational coupling of the black hole. And as they oval, they give rise to this quasi-periodic behavior. Huh. So this is called length-theory precision, and that can be related to the millihertz Qpeo, or the low frequency, not millihertz, but the low frequency Qpeos that are observed in the case of black hole. Now, length theory and precision are a very important consequence of the general theory of relativity, because it is directly related to the space-time curvature and uh, the interrelation between the spin of the black hole on the curvature around the black hole. So this gives you a handle to measure the spin effect on the of the black hole around it, uh, around its neighboring spacetime. So QPOs are still a very enigmatic phenomenon, because we still don't know the complete physics of it. They are related to the bit frequency model, this precisional model just I described to you. They have a lot of advantages. They can be used for constraining the neutron star or the black hole parameters. They can be used to constrain the spin, because, as I just said, that precisional effect is very strongly guided by the spin of the central compact object. So, once you study the precision, you will be able to measure the spin of the central compact object. And particularly for the case of black holes, we know that the mass and spin mostly uh, governs all the characteristics of a black hole, right? So measuring spin gives you an immediate handle to uh, infer the properties of a black hole, study the predict all the behavior of the particular black hole, test various shear effects. Also, such millihertz QPOs, particularly in the case of neutron stars, where there is a strong magnetic field, that can give you the limits on the relevant magnetic field of the central compact object that is present there. And in the case of neutron star, often such QPOs are seen when there is nuclear burning going on the surface of the star. And this can give limits to that as well. There are, of course, just various challenges, like there are the modeling is very complex, and there are a wide source of parameters that are present. No one model can address all the characteristics of the QPOs across all frequencies, and various distinctions have been observed between black hole and neutron star sources, and one need to have a self-sufficient global model to explain all this behavior. Uh, so one final important characteristics of neutron stars are, this is particularly specific to neutron stars, are something called the thermonuclear extractors. So this happens when there's accretion disk around there, and matter is slowly spiraling around the accretion disk and falling on the surface of the neutron star. And as matter gets dumped on, it piles up, and as it piles up, the temperature and pressure at the base of this pile that is creating can reach very high conditions, so that it can initiate a thermonuclear reaction, a fusion process. And as it happens, a large amount of material can completely undergo this fusion process in a runaway avalanche manner, giving rise to such a sharp rise in intensity, and then a very slow exponential decay. So these are kind of thermonuclear explosions that are happening on the surface of a neutron. So these are very exciting, because this is something that is directly happening on the surface that you know. You have to be on the surface to have that conditions which can trigger such a thermonuclear chain. So it's happening on the surface. Because it's happening on the surface, it can give you a very easy handle, most favorable handle to measure the radius of the neutron star, which is one of the most difficult observable to measure. And if you measure the radius, as I told you a little bit earlier, that measuring the mass and radius can give us an idea about the equation of the state. So this gives you an idea about the radius measurement, and also how the thermonuclear flame is propagating and igniting on the surface of the neutron star. There can be a wide variation in the profiles and properties of this burst. We call them bursts, depending upon how much accreted material is getting dumped on the star, what is the material that is getting dumped, whether it is hydrogen or helium or something other, huh, huh, which region of the neutron star it's getting dumped, how fast the neutron star is rotating. All these matters go into the nature of the bursts. Sometimes, often you see uh, two bursts in quick succession, as you can have seen here. This is very rarely seen, and we have seen this in one of our recent works. And this basically tells you that some one event has occurred, and the material couldn't cool enough, and even a small little bit of additional material dumping on triggered a small nuclear reaction chain, which gives result to a little bit low luminosity, but very quickly recurring small burst, which is often seen within few tens of seconds of the main burst. Uh, the thermonuclear bursts, when as they cool down, they are typically well described by a thermal blackbody spectrum. Hmm. The blackbody spectrum can have temperature in the range of 1 to 3 kelvins, and it varies as the burst decays. Here you can see this, as the burst is decaying, how the temperature is decaying, often showing certain increases and decreases, coming from how the photosphere is behaving. And here is the normalization. Here is the how the radius. Let's say the fusion reaction is happening on a localized region on the surface of the neutron star, and as the region spreads, as it spreads, if finally engulfing the entire star, this variation gives you how the radius of the spot spreads. We call that a hot spot, and at the point when it engulfs the entire star, that corresponds to the radius of the neutron star, which will give you a handle to calculate the mass radius relationship of the neutron star, giving rise to strong constraints on the equation of state. Apart from that, during the burst, often one extra thing is seen. As the burst is happening, often it is seen that there is a periodic oscillation that is observed. That is happening only during the burst. It's not present any other time. That's happening only during the burst. This is expected to observe uh, uh, in only 10% of the burst, and happens. It's thought that it happens because there is this localized spot that has been created on the surface of the star where the burning is going on, and as the neutron star rotates, this spot is coming back to you after the end of each cycle, and giving rise to this periodic blip, 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 blip oscillation. And these are called burst oscillation. Uh, and it obviously, the frequency, as you can see, starting from here to here, often shows a quite drastic change even within the duration of the burst, and they give you a handle to measure the spin of the neutron star, which is again a very interesting quantity to totally model the properties of the neutron star. And it also gives you a very good idea about how the flame is propagating on the surface of the neutron star. But actual, real, complete physics of this oscillation is still not understood, and various studies are in process to properly understand why this oscillation is triggered in only certain fraction of the burst, and how we can really use it to totally understand how this burning front, thermonuclear burning front, propagates on the surface of the star. Uh, I probably have only 12 minutes, so let me skip this part. Uh, okay. Another interesting thing that is observed in the case of black holes, and sometimes also in the case of neutron star, but this is more prominent in the case of black holes, are something called the jets. So what happens is that this is the black hole that is sitting there, and it's accreting matter. Matter that is getting accreted is obviously, some of it is engulfed by the central black hole itself, but at certain favorable under certain favorable conditions, some of this matter is thrown away in the strong jets that are perpendicular to the accretion disk plane. Uh, in the cases where the black holes are relatively on the massive side, these jets can be actually imaged, which is was done in this particular case. You can see the jet propagating, and this is basically the highly intense region on the jet as it going slowly propagating outwards. Hmm. So here is the jet propagating, and as it's propagating, different ends of the jet moves further away, and this is very closely related to how the accretion is happening very close to the central black hole, and in the accretion disk, how the differential rotation at different radii distorts the magnetic field, and the distortion of the magnetic field basically ends up giving rise to this very high energy jets. Okay, I will take the last few minutes to talk a little bit different thing. This is about pulses, which I mentioned at the very early first slide. These are also neutron stars, but this is a very special class of neutron stars, which typically tends to have a very higher magnetic field. So here you have the neutron star sitting, and all these lines that you see are the magnetic lines of force, and there's a strong beam of radiation that is getting emitted along this magnetic axis. This is the magnetic axis. And as the pulsar rotates, this is the axis of rotation. And as the pulsar rotates around this axis, if the observer is here, after each rotation, when the pulsar magnetic beam is cutting your line of sight, you will get a blip, blip, blip kind of behavior. So that's why it's called pulsar, because it gives you a pulsating emission. This is one of the first, this class of objects typically tend to have the fastest rotational speeds. And this effect, when the pulsar beam sweeps your line of sight, it's called the lighthouse effect, because much similar to the kind of periodic emission that you see from the lighthouses. They have higher magnetic field. The magnetic field is 10 to the power plus to 10 to the power 13 gauss, which is 10 to the power 13, at least 10 to the power 13 times the Earth's magnetic field, which is one of the extreme magnetic fields that we see in the universe. The spin behavior can go from milliseconds to tens of seconds, and most of these pulses, or the classical pulses, are dominant in the radio wave bands, and this periodic behavior that I just spoke about is very precise, and the precise behavior results in them being the best clocks in the universe. And that's why they are often used like that. This was the first discovery of pulses that you can see, which was discovered by Jocelyn Bell in 1974, and this is the first data that she took of the first pulsar. And the satellite, the telescope that she used to detect the pulsar. Okay, so but the pulse is not just blip, but often the pulse that we see coming from this pulse dances. I just said they are very precise clocks, but even within the pulse, we can see various variations. So here you can see the pulsar is blipping, cutting a line of sight at the end of the cycle. But if you clearly see here, again I will. If you clearly see here, the longitude which relates to the phase of the pulse, this is each single pulse after each cycle, is changing, and it's slowly going like this, and again this, and correspondingly the profile is changing. This is very much related to what is happening at the magnetic pole, at the magnetic axis, and any changes in the charge distribution pattern that is there at the magnetic poles or the magnetic axis results in the such drifting or dancing of the pulses or the subpulses. And a study of this can give you very clear idea about what is actually happening in the emission region from where the radio emission is coming from. Hmm. So this is very interesting phenomenon, and particularly using our own giant microwave radio telescope, which is in UGMRT, the upgraded UGMRT, which is a very large bandwidth. It can observe over a large frequency range. and its sensitivity is also very top notch. Given that this can make it very uh, important instrument to study the behavior of pulses. Here you can see one such behavior that we have observed in our own data. Oops, in our own data, and this is from the same pulsar but at different pulses, for different pulses, and you can see at different points of time how different the dancing pattern can look like. Here it's something different, here it's very smooth, here it's again a little bit smoother, but in a much more sharper way, and that basically tells you how the emission spots that are giving rise to these pulses are changing uh, when the pulsar radiation is beam pattern is cut in a line of sight. UGMRT provides us as a very unique way of looking at such pulse emission behavior that we have seen, particularly in the case of this particular pulse. Uh, as these pulsars are very precise clocks, this also makes them a very unique tool to detect gravitational waves as well. How? Because you know the pulses are coming at particular point of time. You expect the next pulse to come at a particular point of time. Now let's say between this arrival of two pulses, let's say a gravitational wave is passing in between. Huh. If the gravitational wave is passing in between, it will delay the arrival of some pulses at your observation location. And since pulses are so precise, even that small delay can often be uh, theoretically be detected and modeled to infer about the gravitational wave that has passed in between. And this makes them most precise clocks in space. This is that thus these pulsars are a main tool for searching for continuous gravitational waves, and various gravitational observatories like the IPTA, LIGO, Indian Gravitational Observatory Indigo are actively involved in the study of how to use pulsars as detectors of continuous gravitational wave. They can also be used as GPS for interplanetary missions, but let's not go there for this talk. Okay, I will just, before I end, I just wanted to mention one final class of objects which are called the magnetars. These are also a subclass of pulsars, but a different subclass of pulsars. These are not the pulsars I have just talked about, but these pulsars are basically not powered by the rotational energy, but basically powered by the very ultra strong magnetic field that is present for this class of objects. The magnetic field is even higher than pulsars, reaching 10 to the power 14 to 10 to the power 15 Gauss. Rotational period is usually slower because these are relatively newborn objects, newborn after the supernova. So they have not had the time to spin up. Newborn neutron stars are less rapidly spinning. So their magnetic field is such strong uh, strength that it results in a very strong emission powered by the decay of the internal magnetic field. And this is why we see a very strong beam of radiation along the magnetic axis. And as the magnetar, these are called magnetars, and as the magnetar rotates, again much like the pulsar, this magnetic axis cuts your view, and you see a pulse. But in this case, powered by the magnetic field instead of just the pulsar, simple pulsar radio emission. These are thus more observed in X-rays because bright, because of the strong magnetic field, and often such objects are observed along with a series of bright flashes of X-rays and gamma rays. So kind of burst-like flashes. Some of them can be the most energetic. The first such giant flare that was detected, which also resulted in the detection of the magnetar, uh, was an unprecedented event, which was detected when uh, the detector on board a satellite got completely flooded with the emission of with hitting of lots of gamma rays. When the instrument was not even looking at the magnetar. It was looking in a very different direction. But the flash was so bright, it flooded the detector, even which was looking at it even sideways. Uh, So you can imagine how high intense they can be. So these are called flares. They can be from small scale to very large scale, and they happen because of various earthquake-like behavior happening on the surface of the neutron star, or the uh, disconnection and connection, which we call magnetic reconnection of ultra strong magnetic field lines connected to the magnetar. Because the magnetic strength is very high, that results in the emission, which is even very strong. This was the first detection, and here you can see the intensity as a function of time. And within a few tens of seconds, the at the very early stages, the intensity reached very high value, and then slowly decaying to pre-flash values after hundreds of seconds. Such behavior is also seen in small scales. Here you can see it's not as bright as the very high energetic ones, but still you can see such flashes. Uh, and these are also often modeled by thermal emissions uh, as created by the hot spot that is happening in this near the magnetic pole. And as the hot spot cools, which is given by the temperature, this gives you the temperature as the burst, the flash decays, and the temperature can be seen, giving rise to the emission of photons that are coming from these flashes. Uh, Also, along with these flashes, we can see strong X-ray pulsations in X-ray band. These are not radio pulsation, but X-ray pulsation happening due to the internal decay of the magnetic field. And in the case of magnetars, it can tell you a lot about how the magnetic field is behaving. Uh, this pulsation strength varies, and it as it varies, um, just as by studying the pulsation strength, one can uh, infer and model the various changes in patterns in the magnetic field of the magnetar. Often, the neutron star or the magnetar undergoes very strong glitches where there is a sudden spin up or a sudden spin down. This is related to the internal composition, and that can be studied by the X-ray pulsations that we are looking from this particular sources. And and connected to the flaring activities, these pulsations are often enhanced. That tells you how the magnetic lines are related to the uh, physical process that gave rise to the flashes. Interestingly enough, along with these flashes, or even normally in the case of magnetars, we often see line emissions. Here you can see the spectrum of the magnetar, and this dip that you are looking at is cyclotron line. This is happening when the photons that are coming from this magnetic axis, the hotspot near the magnetic axis, interacts with the very strong magnetic lines of force, and undergoes a proton cyclotron resonance phenomenon. And this resonance phenomenon gives rise to a photon that corresponds to the cyclotron resonance energy of the proton cyclotron line, which can be calculated as this. And once we know the energy of the line, we can, using this formula, calculate back the magnetic field of the magnet. And this gives us a way to measure the strongest magnetic fields. And not only that, often we see that the magnetic fields are not as smooth or as dipolar as we have thought, but they are often very complex. And looking at these lines and its complexities, one can map back the complex morphology of the magnetic field of the magnetar. And remember, this is the strongest magnetic field in the universe that is possible. So that gives us a very good insight into the physics of the ultra strong magnetic field. Huh. And finally, uh, there is a. I will just take 2 minutes more. Sorry, Priya. Is that okay?
Yeah, absolutely fine.
One final thing I would like to say is that there is another class of objects that I have not talked about, but which are called gamma ray burst. Yeah, these are not always necessarily related to the class of objects that I have been talking about, but or not to begin with at least. But in certain cases they can be. So gamma ray bursts are extremely bright event in gamma rays that can reach million into trillion times brighter than the sun. And some of these gamma ray bursts are those which last less than 2 seconds. So these are called the short gamma ray bursts. And the short gamma ray bursts, nobody knew what the origin was. The most plausible origin that was proposed was supposed to come from the merger of two neutron stars. That kind of event we have detected in the gravitational wave window. So that was the event that was the origin scenario that was proposed. But soon, with time, that is obviously one of the scenarios. But we soon with time we are seeing that there is another channel that is possible. That some of these gamma ray bursts, as you can see, that one that was detected in April 2020. This was studied by us, and once we look at this particular short GRB, one thing that could have uh, been concluded, that could be concluded, is that this is not related to this scenario, but this is actually one of these giant flares that flare that I was talking about, coming from magnetars. So this gives another origin picture of short GRBs, and it tells us that at least a fraction. There are a few other such candidates. So it tells us that at least few fraction of short GRBs are actually basically magnetar giant flashes, magnetar giant flares. And we could we could show this for the case of this particular short GRB, where you could see the magnetar like um, magnetar flare like thermal decay during the short GRB, and various other properties were also comparable to the magnetar flashes. So this gives us another new avenue where one can talk about the magnetar SGRB connection, which is pretty interesting to understand the origin of this new class of, not new, but a different, distinct class of objects. So I think I should end here. I just wanted to show something. So until now, I have been talking about some results from our very own AstroSat, which is an excellent observatory that gives us uh, opportunity to observe in broadband and in different wavelengths. It's very exciting, and if somebody is interested, a lot of the data is public, and they can look into the AstroSat data archive and start working on that. Apart from that, there have been other observatories that are existing in different wavebands, like NICE, like GMRT, like XMM Chandra, and so on and so forth. In future, uh, this is the current observatory, and each has their own set of advantages. Some has high sensitivity, some has better energy resolution, imaging resolution, better time resolution. So no one, there is no unique answer to which one is the best, but each come up with their own solution of observing this very interesting class of objects that I have been talking about today. And in future, this is the sensitivity picture of this currently uh, current observatories that I have shown here. Huh. So as you can see, AstroSat, Black Species, CZTI, and SX3 fares quite well, but there are a few others that are proposed which are going to do well in different energy bands. And in future, there are various extra missions proposed in different wave bands, like in various missions proposed in different wave bands, like Athena, Shorbex, Pollux, IXP in X-rays, TMT in optical, square kilometer array in radio, LIGO in the gravitational wave bands, advanced LIGO I mean. Hmm. So with them, many other discoveries, exciting discoveries are to come. I hope you get interested by this talk and choose to take part in some of them. Thank you. Sorry for running a little late. Yeah.
Thanks, Manonita, for a lovely talk. a lovely this thing. That was really very nice. You actually went through the whole gamut of compact objects. I see one question's there in the chat window.
Sure.
It says, uh, "Ma'am, does the existence of matter in ultra high densities, what fuels the theory for the existence of a quark star?"
Yeah. So the idea is that if the density goes higher and higher, the quarks that we see, that we think to uh, com- comprise the neutrons and protons, becomes free. Hmm. And they will create a series of quarks. It all depends on the kind of equations of state that you take and the kind of densities that you are expecting. So, assuming the favorable conditions, one can have a sea of quarks that goes beyond the neutron degeneracy conditions, and this free quark matter will balance the, at least at the very core of the neutron star, not in the entirety of the neutron star, at least at the very core of the neutron star, can balance the inward force of gravity. But these have to be a little bit exotic because to reach those exotic conditions, the density has to be even higher. So even higher than in the case of a normal neutron star. So for a quark star, you need the same mass but a much lower radius, which will give you a much higher density. So that will result in such existence of a quark star. I hope I have answered your question.
Yeah. So, Aniket, I hope you got the answer to your question. Are there any other questions? You could put them in the chat window or this thing. I had a question myself.
Yeah, sure.
For all the list of the missions which you gave, right, for the data, I was concerned about the data analysis. That most of them do have their software for AstroSat. Is there a data analysis software already available for LaxPC, SFT, etc.?
So the for the first principle, I mean the first level pipeline processing, yes, definitely. I would give the same answer for all of them. Huh. But for
Okay.
the more advanced analysis, possibly some things need to be coded personally. But definitely for the first standard level products, pipelines are
No, no,
existing.
because like for example, for Chandra, I've used it. The Chandra thing is excellent. You don't need to
Yeah,
almost use anything else, right?
yeah,
That is almost self-sufficient, right?
yeah.
Uh,
AstroSat is not yet exactly like that, but at least it can give you the very standard products like light bulb spectrum, all those things.
no, because I was concerned that in the case when students want to do some projects, etc., they would
Sure.
need to write code also. They would need to do write the code.
Um, for the basic things, no.
Okay,
Basic things can be easily done by the existing pipelines. If
okay,
someone wants to do some very specific things, obviously that requires corresponding modifications or
okay,
corresponding codings.
okay, okay. Thanks, thanks, thanks. Uh, are there any other questions? So, what would be a good way for people to start if they want to, supposing, start doing some projects on AstroSat data? How would they have to do that? How
Uh,
should they start?
yes, so definitely they can start by their own, but obviously that is a little bit difficult for the very uninitiated. Hmm. So sometimes there are workshops going on, definitely organized by the Astroset Science Support Cell. Hmm. They train all the undergraduates, postgraduates, and even very young PhD students to be, um, yeah, to the basic analysis with these pipelines and with Astroset data. And other than that, they definitely can contact all the people that are like us that are working with Astroset data. Data is in principle and the softwares are in principle all openly available in the AstroSet, either the data archive sites or the science support cell websites.
Okay, thanks a lot. Thanks. Uh, I don't see any questions. Please post any questions if you have any. Um, uh, I don't see anything. So, so let's thank Manonita. Thanks, Manonita, for an excellent talk.
Thank
That
you.
was really a very good talk.
It
Thanks a
was a
lot,
pleasure.
and thank you so much. And thank you everyone for watching. And
Thank you, everyone.
see you next. Yeah. See you. Bye bye.
See, bye.